Okay, so I posted this homework 6, and it was all about randomization and Bootstrap and whatever. So here's some things that I think you guys should read, and I've done kind of a little bit of a Bootstrap meta study. Okay, so you can get an idea of how Bootstrap works, but also the dependence that Bootstrap has on the actual sample itself, right? Because the way Bootstrap works is that, well, the way statistical inference works in general is you only see a sample, and based on that sample, we're trying to make conclusions about the population, right? And all of the, the math behind the central limit theorem, all of that is based on the idea of when I do random sampling from the population, what kind of variation appears in my sample, okay? And so we can do a little bit of a meta study by saying we actually have the population, and then we'll take random samples from the population, and then we'll see how our conclusions work based off of our random samples taken from the population, okay? And so in a sense, a lot of what we conclude here should line up with kind of the analytic perspective on the central limit theorem and all of that. But it's kind of neat, I think, to see for yourself how this stuff works, okay? So anyway, I've talked blah, blah, blah about this, okay? So there is a data set in library Bootstrap, okay? There's a data set called Law 82 and law, okay? So Law 82, apparently this represents our population, like the universe. Like if you go to, I don't know how many law schools there are in the United States, but apparently, according to this data set, there's 82 of them, okay? There's probably more, but we're gonna say this is the universe of law schools, okay? That there's 82 law schools, and this is the universe. And we went to each law school and we said, what was the average Lsat score of your admitted class, and what was the average GPA of, the undergraduate GPA of your admitted students, okay? And so here we're curious, what is the correlation between Lsat and GPA? And so in the population, this is what is known. We can go to Law 82, and we can do correlation between Law 82 LSAT and Law 82 GPA. This is the population parameter, correlation of around 0.76. Okay, this is what exists in the population. Now, when you do statistics, we're always dealing with some kind of sample here. Okay, so here we're going to we have the sample law. Law is a sample of 15 schools selected from this 82. Okay, and for whatever reason, when they did law, they took out the decimal in GPA. They basically multiplied GPA by 100. I'm not sure why they did that, but they did. And we can do, what is the correlation between law LSAT and law GPA, okay? And when you take the correlation between this random sample of 15, we're getting a correlation of around 0.77, 0.78, okay? Which seems to be in line here, okay? However, I can just take other random samples, okay? I can just do set seed 1, and what I'm going to do is I'm going to basically sample from 1 through 82. I'm going to take 15, okay? And so these will be the 15 schools that I select. So I would do Law 82, and I'm going to, let's go back to set seed 1, and I'm going to basically just subset Law 82 right here using those 15 rows, sample 1 through 82, 15, those 15 rows. And Law 82 has 3 columns, and I really just want columns 2 and 3, okay? So that's what I'll do here. So this will be law underscore sample 1. I do that, and I do law samp 1 and we can calculate, I'm sorry, we can do the correlation between Lsat and GPA in LawSamp 1, okay? All right, and when I take the correlation between these two, I'm getting a correlation of around 0.95, okay? So this is drastically different, and this is just another random sample of 15, okay? And just to kind of give us an idea of these things, let me just plot all of Law 82. So this would be, we're going to plot LSAT versus GPA. Oops. Okay, so this is all 82 law schools, and when we do just the selection of 15, this is law, and then but if I do LawSamp 1, okay, and this is just because of random sampling, you know, we see, okay, you know, the correlation here is a lot stronger in this random sample, all right? And so, you know, if I take a different random sample, I'm going to do set seed 2, and I'll do LawSamp 2, just again sampling 1 through 82 to select my rows, and I calculate the GP correlation there. I'm getting a different number, 0.627. And then here I'm going to do set seed 10, and if I calculate the correlation there, I'm getting, you know, 0.8177. So we see our correlation can end up, you know, kind of all over the place, just depending on the random sample of 15 schools that I select out of the population. And so what we can do is we can do kind of this meta study to see how you know, different samples from the population would affect our values here, okay? And so in general, when we're dealing with something like this, probably the value we're curious about would be the standard error, okay? Because when you have the standard error, then you can start doing some inference about your observed correlation R, okay? So we're going to do some inference about the observed correlation R on the population correlation rho, right? So, you know, that's all of inferential statistics. You have your sample statistic. Based on what you see in your sample statistic, you're trying to make a conclusion about the population parameter. So in here, our sample statistic is the correlation R, and we're going to try to make a conclusion about the population correlation, which would be rho, right? Using the Latin versus Greek letter correspondence thing. Okay, and I don't know if you remember the estimated sample error for the population is 1 minus rho squared divided by the square root of n minus 1. I don't know if you guys learned that standard error of the correlation. Okay, but anyway, let's try this out. So we have, oh, this is acting a little buggy here. We can use this. All right, so if I were to do manual Bootstrap, I can do, we'll just take our random sample law, and we'll do, oh man, something's going on. Okay, so I'm going to do 500 replications. We're going to say, we know n row is going to be 15, but just so it works out, we can see we have 15 rows. And then we're going to store our results of our Bootstrap. This is to calculate the standard error. We're going to just create a vector for results, okay? And so I'll do set seed 1, just to kind of set our random seed, and we'll see if I can get this. Okay, and I'm going to repeat this 500 times, and basically, so this, I am not resampling from the population. Here I am sampling from law itself. So remember, law is this group, random sample of 15, and the current correlation between law LSAT and law GPA typo, is 0.776. Okay, so I'm going to do Bootstrap resampling on this group of 15. Okay, because again, in Bootstrap, you're taking your small sample and you're going to sample with replacement, which basically you're making an infinite number of copies of this sample, and you're treating that as the population. And so, of course, depending on which sample you have, it's gonna affect it, what you conclude. But anyway, so here we're going to take this 15, treat this as my population, sample with replacement. Okay, so we're going to sample from here with replacement, and then we're going to extract the Lsats, extract the GPAs, and we're going to calculate the correlation between Lsat and GPA. Okay, and so when I do this, I would expect all of these results to be close to 0.776, which is the correlation I see in my sample. And so, so here's my loop. I run that. Okay, and so my results vector has 500 values in there. I can ask what's the summary of my results. Okay, and we get a mean right around what I expect, 0.767. But the smallest correlation that I end up is quite small at 0.048 and up to 0.986. Okay, and the standard error would just be the standard deviation of this results vector, right? And so here I'm getting a standard error of around 0.13, 0.14. Okay, so this is just an estimate of the standard error by doing Bootstrap resampling on this sample of 15 law schools. Okay, and this sample of 15 is taken from the population of 82. So here we get a standard error of around 0.13. If I wanted to use package boot, all right, I would have to create a function to calculate the statistic that we want, right? So over here, I'm storing the resulting statistic, which is what I want, into this results vector. With package boot, I would create a function to do this. So this pretty much follows the same form that I had before. I would subset my data using the indices produced by boot. We're going to extract Lsat, extract GPA, and calculate the correlation between Lsat and GPA. Okay? Or if I wanted to just make that a little bit more concise, these two things do the exact same thing. Just in one line, I've got correlation where I'm subsetting data on the index, taking the first column, correlation of taking the data with the index and taking the second column. So that's just the way to do that. And then I can load up library boot. And to run this, I just do boot. We're going to take our law data set, which is the 15 law schools, and we're going to do Bootstrap resampling on that sample of 15 using the correlation function, and we'll repeat this 500 times. Okay? And here I can estimate the standard error again by taking a look at results $t, and when I do that, I get something very similar to the other results I got of around 0.13. So these two things are in alignment, just because of sampling error, they're a little bit different. Okay. So we could try running the same thing, but this time using some of the other samples that I looked at, right? So LawSamp1, if we remember the correlation of LawSamp1, we saw LawSamp1 just happened to have a very high correlation between these two things. Okay, so here I can run Bootstrap there, and then I can ask what is the standard error on this estimate. Okay, and so when I do the standard error here, I'm getting a standard error of only 0.025. Okay, and then we'll just try this with some of the other samples. LawSamp2 had the relatively low correlation. Okay, and then so when I ask for the standard error on this one, I'm getting something a little higher, around 0.15. And then LawSamp10 was something in between. I can ask what's the standard error here, and I'm getting something around 0.05. All right, and so our estimates of standard error depend heavily on the original sample. Okay, if I did so let me just show you. If I just reran this Bootstrap here, reran the Bootstrap another 500 times, and I calculated the standard deviation there, we see that the Bootstrap itself produces results that are fairly consistent within itself, right? Because it's doing 500 replications, and it's trying to estimate the standard error. Each time I do this, these results are fairly consistent, okay? However, the results between estimates of standard error vary dramatically depending on the original the sample that I drew from the original population, okay? And that's really kind of the bane in statistics, is that whenever you do random sampling from the population, because it's random sampling, in the long run, it should work. But when you look at one sample, you have no idea if this is a quote good or a quote bad sample, okay? It could be the one that has really high correlation. It could be one that has correlation right around what the population is, which is what you're always hoping for, or it could be one that has correlation that's really low. You have no idea, okay? Bootstrap is a useful tool in estimating kind of the standard error based on the sample that you have, but it's only going to be as good as the sample that you have, which according to probability theory, I don't know what's going on with my notebook here. I hit these little X's? That seems a little strange. Okay, well, should work out. So here I'm going to do a little bit of a meta study. Okay, and so what I'm going to do here is I'm going to do this 1,000 times, and this is going to take a little while to run. Okay, but every time I do it, what's going to happen is I'm going to draw a new sample of 15 schools taken from Law 82. Okay, so from our universe of 82 schools, I'm going to draw a new sample of 15 schools. Okay, and we're going to call that Law Samp. Then I'm going to run Bootstrap resampling on that sample of 15. Okay, and then from that we're going to take a look at, get an estimate of the standard error. Okay, and then we're going to do this 1,000 times. So we will get an idea. So each time I'm going to run it, basically the first 3 times I run it, or the first 2 will, I'll get the standard error around 0.025, and then the next one will be around 0.15-ish. We're going to just do this over and over and over again. We'll do this 1,000 different times. So here, the advantage of the meta study is that I've got the actual population to work with. I can draw 1,000 different samples of 15 from the population and see how that affects the standard error that I'm looking at, right? So we can kind of get an idea here. So does this make sense what I'm doing here? We're trying to see the effect of random sampling on our estimates of standard error based on Bootstrap. Okay, so I'm going to just run this, and it's going to run. So every time I'm setting a new seed, I'm drawing a new sample from the population of 15. Using that sample of 15, I'm going to do Bootstrap to get an estimate of the standard error. Yes, question? Yeah, in reality, we only have one sample. So this is the point of this meta study is to see how dependent our estimates and our conclusions are on the nature of the random sample. Okay, and so this should give us a better idea. And okay, and so here I've got it's done running. We have 1,000 estimates of what the standard error is. So we can kind of see the summary here. And so this is what it looks like. Our standard error ranges anywhere from around 0.03 to about 0.4, okay, which is which varies quite a bit, our mean standard error is around 0.126, okay? According to kind of some of the conclusions based on, central limit theorem stuff, if the population is assumed to be normally distributed, our standard error should be, our population correlation is 0.76, so if I calculate this, my standard error should be something around should be around 0.112, okay? And we're getting something kind of close to that, 0.126. And then we can kind of just plot a density estimate. Oh, why is this doing this? Okay, this is what I want. Okay, and so we see, yes, indeed, our standard error estimates are centered around where they should be, okay? But we do get things that are low and things that are high, and we even got one that was unusually high, okay, for our standard error estimates. And this is just after 1,000 replications, but we get something that looks kind of like this. So this gives us an idea of how how our estimates of standard error, if we're using Bootstrap, how that depends on the random sample itself. Okay. So that was kind of the worked through example that I have. You can read through that. I'll post, and I did some additional stuff. Okay, and so I'll go over that here. Okay. So another thing that we might use statistical inference for is comparing proportions between two groups. Okay. So here I'm going to, and we can. This is an entire other thing to discuss. Okay. And so, well, anyway, all of this to say we can do a bunch of meta studies to get an idea of these things. So here I'm going to create two populations. Okay, I got population X and population Y. Population X has 700 ones and 300 zeros. Population Y has 600 ones and 400 zeros. Okay, and I could, when I sample from this, I could sample with replacement, so it's not just a finite population of 1,000, but technically a an infinite population, or however I can treat it however I want. Okay, and I'll combine them all into a data frame, and here's let's call this. Let's call it that, okay? So I've got, X has a proportion of 70%, Y has a proportion of 60%, okay? And so let's say we wanted to do some hypothesis testing here, okay? And so if we were to do hypothesis testing, we would draw a sample from our populations, okay? And then we would say, okay, the proportion in sample 1 is this, the proportion in sample 2 is this. Does this provide evidence that the populations have different proportions? Okay, that's what we would be asking. And we know, because we see the population, we know that there is a difference between the proportions and the population. In the population, one has a proportion of 70%, the other group has a proportion of 60%. Okay, and we want to know, can we detect this? How well can we detect this? And this is a bit of, we might be doing some power studies and seeing like how big our samples need to be. We can kind of do some of this doing a little bit of a bootstrap study here. Okay, so here's my thing. So what I'm going to do is first we'll just try one example here, right? So we'll do set seed 1, and the way the data frame is set up is if I look at it's just I've got Z being ones or zeros in the group, and it's all in and there's 2,000. I think the first 1,000 is group X, and then the second 1,000 is group Y. Okay, and so in here I want to when I draw my random sample, I want to get 100 from X and 100 from Y. Okay, so I'm going to sample rows 1 through 1,000, and I'm going to draw 100 from them. And then I'm going to sample rows 1,001 through 2,000, and I'm going to draw 100 from there. Okay, and that will give me 100 rows from X and 100 rows from Y. Okay, I could turn on replace equals true if I wanted to treat these as infinite populations, and that might be something worth exploring. Right now we'll just say we've got a finite population of 1,000, and we're going to take 100 from each of them. And then we would subset our data by using those indices that I selected. Okay, so I would do data and subset based on the indexes, and so this would be my SAMP. Okay, and so I can ask what are the dimensions of SAMP, and I would have 200 rows, 2 columns, and I can create table SAMP, and I'd see, okay, I ended up getting 72% X and 61% Y. Okay, out of 100 I got 72, and over here in Y I got 61. And so the question is, so first of all we can calculate the difference between proportions, right? So this would be 0.72 versus 0.61. We would get a difference between proportions of 0.11. This is just kind of the way to calculate that. I would take SAMP $Z, which is the ones and zeros, subset those based on the ones that say group is X, and take the mean of that. This will give me 0.72. I would do the same thing over here where the group is equal to Y, and I would get 0.61. And so when I calculate the difference between those, I'm getting a difference of 11%. Okay, so this is our observed difference between proportions. So if we were to do Bootstrap for a hypothesis test, okay, our null hypothesis would be that group X and group Y, the proportion of group X and the proportion of group Y have no difference between them. That would be our null hypothesis. Okay, and so under the null hypothesis, I could just throw all of these, all 200 observations into one population, sample from those, and then split those up into, put the first 100 in group 1 and the second 100 in the other group, and then just calculate the proportional difference between those two things. Okay, so if the null hypothesis were true, then the observed difference would be this. I would just resample from the 200 and throw the first 100 in one group, and I would throw the second 100 in the other group. And so this would be the difference between proportions if the null hypothesis were true. Okay, and so we do that, and then I can just run Bootstrap there. And to get an estimate of our p-value, I would find how often did the differences between proportions from our random resampling end up bigger than our observed difference of 11%. Okay, that's what we want to know. Okay, and so we do this, and I'm getting a p-value of around 0.054. Okay, just a fraction over 5%. So if my observed difference is around 11%, I would get a p-value of around 0.054. Okay. Does the thinking there make sense, or do we have any questions here? So here I'm basically conducting a hypothesis test by saying, under the null hypothesis, everything is in the same group. We're going to just resample them and just shuffle them out into group 1 and group 2, and then see if they have a different proportions there. Okay. You could do something similar with a randomization study if you had used random assignment for the things, but here we're treating these as we're drawing from the population. Okay, so we do this, and and we get 0.054. And then so maybe we want to do kind of a meta study and just say, okay, what if I had drawn a different sample? Okay, so this sample that I drew here looked like this with an observed difference of 0.11. What if I drew a different random sample and I had a different observed proportions? Okay, or different difference between proportions. Okay, so if I drew a different random sample from my population, how would this affect the resulting p-value that I get? Okay, and so this takes a little while to run, so I'm only going to do 200 replications of this. Okay, but I just want to show you what I'm doing in each time. It's pretty much what I did right here, but it's all put together. So I'm going to set a new seed. When I set the new seed, I'm still going to draw 100 from the first 1,000 rows and 100 from the second 1,000 rows. Okay, that's going to give me a sample of 200. And from that, I can calculate the observed difference between those in group X and those in group Y. Okay, I'm calculating, you know, what proportions are 1s and 0s in group X, what proportion is 1s and 0s in group Y, or just what proportion is 1. And then we're going to do Bootstrap resampling on my sample of 200. Okay, I'm going to do Bootstrap resampling on my sample of 200. Maybe for speed, I'm going to just reduce this to 500. Okay, we're going to do 500 Bootstrap samples of this. Each time we are assuming that the null hypothesis is true, saying that they're all coming from the same population. We want to know how often does that produce a difference that is greater than or equal to our observed difference. Okay, and so this would be kind of our empirical p-value that we're going to record. And we're going to do this 200 times and get an idea of this. Okay, so I'm going to create a bunch of p-values. We're going to repeat this 200 times. It takes a little while to run. And then when we're done, we can see, you know, how often would we be rejecting the null hypothesis, okay? If we're using an alpha of 5%, okay? So what is this? When we're calculating how often we're going to reject the null hypothesis, this quantity would be known as our what would it be called? This would be known as our power, right? What is power? So power is the probability of correctly rejecting the null hypothesis, right? So remember when we've done the bootstrap, the bootstrap was done with the null hypothesis being that P1 is equal to P2, okay? And we know that this is wrong because the population has P1 equal to 0.7 and P2 equal to 0.6. So we know that that's wrong, but we just want to know if I took a random sample of 100 from each group and I did this, how often am I going to be rejecting the null? Okay, so this is kind of like using Bootstrap to do a power study. Okay, now I think, is it 101B that you learned power calculations? 100B? Oh, okay, so in power calculations, you know, we can do this, and so we do this. So this says I have a power of about 40%. Okay, that's not that great, right? That means more than half the time you're not going to detect this difference between populations. Okay, so what are ways we can increase power? Oh man, we don't. Okay, increase the sample size. That's probably our biggest number one way, and then the other way is increase the risk of type 1 error, right? So if I just, the easiest is just to increase our alpha. That increases our power, but it also increases our type 1 error. So if I increase alpha to 10%, now my power goes up to 0.535, which I would say this is, the change in power here might not be worth the change in alpha here. Okay, so but we can get it. This gives us a direct idea of how much we're improving things. Okay, so here we can try. We can do this again, and so we can say, well, okay, well, what if instead of taking samples of 100, we took samples of 200 from each group? Okay, and we can just kind of see what happens there. So in this case, I would do 200, and then from 201 to 400, and then when I run my samples, I would have to do 200 and 400. I would probably, I'm going to turn on replace equals true for drawing my original samples. Okay, and then still we'll just repeat this 200 times. Okay, so we'll say that's our thing. P-values, reset that. Run this 200 times. And then we can see how much our power increases by taking larger samples. Samples of size 200 rather than 100. We'll see how much our power improves. Over 40%. Maybe we get a lot of improvement, maybe we don't get that much improvement. Okay, and then so these are all questions that you can try to get at when you're planning out a study or something like that, right? So here we're trying to detect. This is assuming that the population has what we call an effect size of 10 points, right? So population 1 has 70%, population 2 has 60%. How often can we detect that difference? Over here, if that effect size was greater, we can see what would happen. If that effect size was smaller, we could see, how much bigger does our study need to be. So in this case, so by taking samples of size 200 from each thing, my power goes up to around 66, 67%. We can see, if I combine this with increasing my alpha to 10%, this changes, and maybe this is satisfactory to us, maybe it's not. But we can, all to say, is we can get an idea of how much power, or just the effect. By altering our sample, we can see the effect that the random sample has on the types of conclusions that we make. Okay, because that's a huge factor, is when you're taking random samples. And so I was debating whether or not we could look at some election polling data and just see do some meta studies there, but it got a little complicated as I was trying to trying to work it out. I wrote some code for possibly doing the Bootstrap manually, but it wasn't actually any faster. I was hoping it would be a little bit faster. Okay. I was also going to take a look at exercise 1 and in chapter 6 and in chapter 7. But I think I'm going to run out of time to actually kind of cover this in the detail that I want to. So I'll write the solutions for this and post them online for you guys to take a look at. So you guys have your final exam on Tuesday, and I'm still finishing up writing it. Again, I'm trying to err on the side of making it easier than too hard, but I don't know, right? That's always, well, anyway. So, but bring a ruler, bring a calculator class. There will be a little bit of manual work, and I'll probably have you write a little bit of code for doing some Bootstrap or randomization tests. Okay. All right. Well, anyway, it's been a pleasure being your teacher this quarter. I hope you've enjoyed the course, and I'll see you guys at the final. And have a great New Year. So.